So this is the 8th lecture on continuity. Today we will start with discontinuities. Discontinuities of a function. Now discontinuity can happen many ways. Like these two functions are coming at the same height, but the functional value at that point is defined to be something else. So this is one kind of discontinuity. This is another kind. This is like you and your long lost friend have decided to meet, but forgot to mention the place where to meet. So you have reached here, your friend has reached here, so you cannot see each other. Here you both can see each other, but you cannot meet each other. Fine. So these are simple discontinuities. Now this one is also there. There are too much of oscillation. Okay. This is Dirichlet function. This is too much of discontinuities everywhere. And we have this kind of discontinuities as well. Okay. So the same kind of oscillatory discontinuity, but this oscillation is going to be infinite. And here it was kind of in control. So these are different kinds of discontinuity. We'll get into all of them one by one. Now let us see the definition of discontinuity first. This was the definition of continuity, if you all remember. Then negating that there exists epsilon naught such that for all delta positive there exists a violatory point x delta in the delta neighborhood of C intersection D, of course, such that if x delta minus SC is greater than epsilon naught. So that means the behavior of the functional value at that violatory point x delta is something outside of our error bounds. F can have a discontinuity at a point C only if C is a limit point of the domain, and of course C belongs to D as well. Now understand this thing, that if C is not a limit point of the domain, then it is an isolated point, and in that case a function is always continuous at some isolated point of the domain. It cannot be an isolated point of the domain for the function to be discontinuous. So the point has to be a limit point of the domain. Now, whenever we have got limit point of the domain, that means we can talk about limit of the function at that point. Depending on how crazy these fx deltas behave, we have different classifications of continuity. We start with this one, type 1 discontinuity. Let f be discontinuous at a point C in D. F is said to have a type 1 discontinuity if both, or the one which makes sense, the one-sided limit fc plus and fc minus exist finitely. The first two are type 1 discontinuities. Let's see the definition once again. So the type 1 discontinuity is something within our control. The limits of both sides of the function exist. The function is bounded, function is approaching to a certain value. So the function is well behaved in a neighborhood of the point. So this is the left-handed limit, this is the right-handed limit. They exist. And in this case, they are even same. In this case, left-hand limit and right-hand limit both exist, but they are not same. Both of these two are called type 1 discontinuity. Type 1 discontinuities are better behaving discontinuities. Now, I put something in the bracket over here, or the one which makes sense. What do I mean by this? If this point C happens to be the extremity over here, then there is no point of talking the left hand limit at A, because that is outside the domain of the function. In that case, considering about the discontinuity at this left extremity, we want to only see whether the right limit at that point exists or not. Next we have type 2 discontinuity, where all crazy things can happen. So if f is said to have a type 2 discontinuity if at least one of the one-sided limits does not exist finitely. This is type 2 discontinuity, and that covers all these things. Let's see more about type 1 discontinuity. First category under the type 1 discontinuity is a removable discontinuity. So the first figure that you saw there is a removable discontinuity. F is said to have a removable discontinuity if the limits exist at that point, but the functional value is not same. Limits exist means the both one-sided limits agree at that point, but the functional value is something different. So you can see your friend but not meet her. We can remove this discontinuity of this function a by redefining the functional value as this point. So we can just bridge this gap by defining the functional value as this common value of the limit of the two one-sided limits. So it is like fx is equals to x when x is greater than 0, 1 when x is equal to 0, and minus x when x is less than 0. So it goes this way, this side, and this way, this side. So this is modulus function. Now at 0, the function is defined at this point. So this is the removable discontinuity. This branch is coming to this side, this branch is coming to this side, but the functional value at this point is at this point. So there is no point over here. The function value is at this point. Now we can always redefine this function to be 0 over here. Then this point comes back to over here and the function, everything becomes continuous. This seemingly easy remark needs a bit more attention. What is so casual about removing the discontinuity by redefining the function? After all, you are changing the definition of the function. Why don't we consider that a serious issue? The answer is the change is happening over a portion of the domain whose length is 0, not negligible or almost 0 or very small or nothing like that, but it is exactly 0. If in case of the other function where the limits from both sides do not match, we want to join the two sides by pulling them towards a common point. So you just stand here and you pull this side from left and this side from right and try to join them at a common point. If you want to do that, we cannot do it over a 0 length portion of the domain. We will be bending this one from say over here to come over here and bending this point, let's say, to join over here. So we need to bend it. We need to alter the definition of the function over a portion of the domain with strictly positive length. This reason is more suitably explained in the measure theory, which you will study in your postgraduate course. And if we borrow a terminology from measure theory, the function after removing the removable discontinuity is the same as the original function almost everywhere. This almost everywhere is a terminology from the measure theory. So over here, this function and exactly mod x function everywhere, these are functions which are equal almost everywhere. Next, we have jump discontinuity. So very easy to understand. Jump discontinuity at a point is the left-handed limit and right-handed limit are not same, and the value, the right-handed limit minus left-handed limit, is known as the jump of f at c. So this is the jump of f at c. Okay, this is pretty straightforward. Jump is something you will in the greatest integer function, the step function. That is, the jump is there at every integer point. Next, we have type 2 discontinuity. So this is the first category of type 2 discontinuity is finite oscillatory discontinuity. This is finite oscillation. So this is the graph of sine of 1 upon x. So around 0, it oscillates very rapidly, but the oscillation is finite. So it's from here till here. This is the entire oscillation. It doesn't go outside of it. So this is finite oscillation. It cannot reach to a certain height. At around this point, it will oscillate vigorously, but the oscillation is finite. Now the definition, if you say to have a finite oscillatory discontinuity at a point, if at least one of the one-sided limit, the left-handed limit or the right-handed limit, does not exist finitely, but f is bounded in some neighborhood of c, then the oscillation will remain finite. Now let us see these quantities. Let us agree to use the following notations. Fc plus overbar is the limit superior of the function f as x is tending to c from right. Fc minus underbar is the limit inferior of the function f as x is tending to c from right. Fc minus overbar is limit superior of the function f as x is tending to c from left. And similarly, Fc minus underbar is limit inferior of the function f as x is tending to c from left. Now, why are we considering these quantities? Because one of these limits does not exist, so we are looking for the lim sup and the lim in. Also called MFC, capital MFC, as the maximum of all these four quantities, and small MFC is the minimum of these four quantities. Then the quantity capital MFC minus small MFC is finite because the function is bounded and is called the total oscillation of f at c. Now, example. So this is the function f is equals to sine 1 by x. So here you see at 0, I have just drawn the function on only one side of the y-axis. The same thing will be reflected on this side as well. Around 0, the lim sup is at this height. It is 1. The lim sup at the right-hand side is also 1. The lim sup of the left-hand side will also be 1. Lim in from the right-hand side will be minus 1, and lim in from the left-hand side will also be minus 1. Hence, the total oscillation of f at 0 is 2. So now you understand this thing, that this is the total oscillation of the maximum of this thing and the minimum of this thing. So on both sides taken together, this is the total oscillation. Next, we have infinite oscillatory discontinuity. F is said to have an infinite oscillatory discontinuity at a point if at least one of the one-sided limits doesn't exist, even infinitely. And f is unbounded in every neighborhood of c. it will look like something like this. This is 1 upon x sine 1 upon x. The graph will go this way. This one, the border of this graph is 1 upon x, and the sine 1 upon x is oscillating between the 1 upon x values. So this is 1 upon x sine 1 upon x, infinite oscillatory discontinuity at 0. Okay, the finite and infinite oscillatory discontinuities are often called as essential discontinuities. Infinite discontinuity, the next one, is said to have an infinite discontinuity if both one-sided limits exist infinitely. This one does not exist even infinitely. This is so rapidly changing up and down, but in this case, this exists infinitely. So this right-sided limit tends to infinity plus infinity, left-side limit tends to minus infinity for the function 1 upon x. So this is an infinite discontinuity, but these ones are infinite oscillatory. Now, popcorn function defined about 0, 1. At 0 it is 1. At the rational point, where the rational point is m over n, that is 1 upon n, and it is 0 at the irrational point. Now, consider the sand as the irrational point and the cones before they pop, cones as the rational point. So here you consider the sand as the irrational points and the cones as the rational points. Over here, the functional values at that point is jumping suddenly. The sand particles are staying there. So the value at the irrational point is 0, and at the rational point is something positive. So let A be any rational point in 0, 1. Fine. So then if at A is 0, because at rational points it is something positive, 1 upon n, and at 0 also it is 1, so it is strictly positive. For every rational value point, the functional value is strictly positive. So it is the popcorns which after it pops and jumps out, so it is at a positive height always. Considering a sequence of irrational numbers converging to A, we see that f of qn tends to 0, because f of qn is always 0. Qn is an irrational point, so f of qn is always 0. Think of it in this way. So you have the corn and the sand particles mixed together. Then you can approach to any corn particle through the sand particles. After it heats up, the functional value at the rational point is at some positive height, because the corn has popped to a positive height. Therefore, the function is discontinuous at that point by sequential criteria. The functional sequence is converging to 0, but the functional value is strictly positive. So the function is discontinuous at the point A. A is any rational point, so consequently it is discontinuous at every rational point in 0, 1. Next, let B be an irrational point. Fine, let's see what happens. Choose epsilon arbitrary. By Archimedean property, we get a natural number k such that 1 upon k is smaller than epsilon. No problem. Now, observe that this set, the set of all rational numbers in 0, 1 with the denominator maximum as k is finite. If I arrange the rational numbers in this way, it will be 1 by 1, then 1 by 2, then 2 by 2 it is already taken, then 1 by 3, 2 by 3, 1 by 4, 3 by 4. This way if we continue, then you realize that in this way we will be able to list down all the rational numbers in 0, 1. Then you see the rational numbers with denominator less than or equal to 4 are only finite. 1, 2, 3, 4. And out of this, 1, 2, 3, 4, 5, 6, 7. This one is common, so only 6. If I add 5 there, 1 by 5, then 2 by 5, then 3 by 5, then 4 by 5, this way. So the number of rational numbers with denominator less than or equal to 5 are only this many. So they are finite. Okay, in this arrangement, there are only finitely many rational numbers with denominator smaller than a given number. So this is what is happening over here. M over n, the rational numbers we are talking about in 0, 1 with the denominator smaller than or equal to this number k. So this is a finite set. Now this delta, which is minimum of the points of, there are only finitely many points, so I am talking about finitely many quantities over here, x minus b. Now definitely b is not there in S, b is an irrational number and this is a subset of rational numbers. So x minus b, this is a strictly positive number, this delta. Okay, so this is the distance of b from the set S. S is determined by the chosen epsilon and this k, which you get by Archimedean property. Now, the delta neighborhood of B does not contain any rational number of the form m over n with n less or equal to k. Delta is the distance of the point B from the set S. Every point from S is at least delta distance from B. So therefore, this delta ball around B cannot have any point from S. But S contains all rational points with denominator smaller than or equal to k. Hence, the delta ball around B cannot have any rational point with denominator smaller than or equal to k. Consequently, for any point, any arbitrary point in the delta neighborhood of B, intersection 0, 1, we have fx minus fb, the distance. When x is a rational point, then fb is 0. So this is fx. So fx is 1 upon n if x is n over n. Now this n, we have guaranteed that n is greater than k. So 1 upon a is smaller than 1 upon k, and 1 upon k is smaller than epsilon. So for rational points in the delta neighborhood of B, we have the distance between fx and fb is smaller than epsilon. And if x is an irrational point, then it is 0. This is also 0, this is also 0, if x is irrational. So therefore, for every point in the delta neighborhood of B, intersection 0, 1, the distance is smaller than epsilon. This is epsilon for rational point, 0 for the irrational point. So the for any point, the distance is smaller than epsilon. That means the function is continuous at B. The function is continuous at every irrational point in 0, 1. So the function is discontinuous at every rational point, continuous at every irrational point. This is this kind of a peculiar function, this popcorn function is. So this is your exercise.